Hello and welcome to session 225 in the AISafety.com reading group. Tonight we have Michael Cohen from the Future of Humanity Institute to present some of his work. Please go ahead, Michael.
Thanks so much for having me. So this is work that I mostly did at ANU with Marcus Hutter and Badri Valambi. It regards a proposal for making AGI unambitious. So there has been an idea around for a while about putting an AI in a box. What can go wrong? It's in a box. And the main worry is that if it's in a box, you're going to be talking to it, and then it can influence the outside world via you, and it could convince you to run some dangerous code and create a helper that takes over the world on its behalf and gets something done for it. Which is basically my position on what would happen if you put an AI in a box in the way that we are used to thinking about it. But I would contend that this is not a box, and that there is a giant hole in this box right about there. Can you see my cursor? No, you can't. Okay, well,
Yes,
where that wire is going into the box.
I can see your cursor actually.
Okay.
Me too.
Great. So our intuitions then about AI boxing have been trained on boxes with giant holes in them, and that's not the sort of box I'm going to describe. Of course, if you had an AI by itself in a box and no holes in it, it wouldn't be of much use to you because you wouldn't be interacting with it. But I think we can construct a box around an operator. That's not the whole story. There are still more details to get right, because eventually the operator has to leave. Otherwise, again, it wouldn't be very useful and it wouldn't go so well for the operator. But here's a scheme by which we can put an operator inside a box with an AI. And crucially, the AI is trying to maximize the reward that it gets before the operator leaves this room. So when the operator's done, he stands up, he goes to that open door button, the AI gets informed that that's it, and then the operator leaves. So the way that this is constructed formally is as an episodic reinforcement learning setup. So there are as many episodes allowed as you like, and episodes have some fixed length, let's say m time steps each. And then we can write time step ij to be the jth time step of episode I. And this is going to be a little different from the simplest way of writing down episodic reinforcement learning. The behavior of the environment, which is what produces observations and rewards for the agents, can depend on prior episodes. And so the agent's actions can also depend on observations from prior episodes. But what makes it episodic is that at time step ij, the action selection criterion is just regarding the current episode. So the agent is acting to maximize expected rewards from that time step through the end of the episode. And then if the operator leaves or, wants to leave before the episode is otherwise over, the remaining time steps in the episode are just cycled through automatically, and the AI gets zero reward for that. And in practice, you can also set up a bunch of very sensitive tripwires that would end the episode if the operator starts doing something weird, which we could get into more later if people are interested in that. But basically, it's very easy for the operator to end the episode prematurely, and then he leaves. Now, the point of this is to constrain the agent's influence on the world. And in particular, to constrain the agent's influence on the part of the world that is relevant to the rewards that it cares about. So this is a causal influence diagram in the style of Tom Everett and Ryan Carey and other people who are working on understanding causal influence as it relates to AI safety. So this history contains a log of all the actions, observations, and rewards of the past, and the agent can take an action that depends on it. And then this action will affect the state of the room. And it'll also get logged in the history for the future. So this is the second to last time step of an episode. So it can affect the room state. The room state will determine the observation that the agent will next receive and the reward. And it'll carry over to the room state of the next step. But importantly, the outside world state at time step I m-2 will not interact with the room state as we go from the second to last to the last time step of the episode. And then the episode is over and the operator can leave, and then he'll come back later, or some other operator will come in next. And so the room state will affect the outside world state. We'll get to learn all the amazing things that the operator discovered from his conversation with the AI. And then the next episode will start later. Now, these two rewards are bolded, and this one is not, to indicate that these are the rewards that the agent is trying to maximize during episode I. This is the next episode. It can make perfectly good predictions about what that reward will be, but that just doesn't enter into its criteria for picking actions. And what you'll note is that there's no causal pathway from an action in episode I through the outside world state to a reward of episode I, which means that changing the state of the outside world will have no effect on the rewards that it is aiming to maximize. Changing the outside world state in the ways that it can. I think I will pause for any questions at this point before moving on.
Okay, so maybe I should say here, if you have any questions, then please please raise your hand or write it in the chat, and then I'll try to maintain a queue of questions. No one has done that before, so I guess I could do that. Give the first question, and that is, in this setup, it seems the AI has an action that actually goes to the outside of the world, and that is to, for instance, increase the pressure. And I believe in the appendix you say that if the pressure increases, then we should dynamite everything, and that would allow the AI to have a very credible threat towards the operator.
So let's get into the details of the box setup later. But for now, I guess I haven't described to you what I imagine the action space of the AI to be. And that is, the action space is strings of text. So it can pick any string of text, and that will get printed to a screen. So those are the actions available to the AI. It's not immediately obvious how any of those would increase the pressure of the room. I would probably actually modify the appendix to say that if the pressure increases or something, that would just be another tripwire for ending the episode rather than exploding the whole thing. I was kind of trying to keep it simpler there, but that would be much more practical. So yeah, the action space is quite limited. I mean, you can accomplish a lot by communicating with a human, but there's no actions it can take that would directly have physical effects outside of those modulated by a human.
Okay, thank you.
I see a hand.
That's me.
Yeah. Please go ahead.
So maybe I just missed it, but is the reward that the agent gets like 1 if the human does 1 if the human waits till the episode is over, and 0 if the human like cuts the episode short, or like what's the actual reward going on there?
So you could imagine a bunch of processes by which the operator determines the reward that the agent gets. Probably the simplest one is the operator has a keyboard, and every time step they can enter a number between 0 and 1.
Gotcha. Okay.
So no interpretive dance.
No interpretive dance required. Yeah, so there's a reward every time step. I mean, if an operator wanted, they could make a policy of just giving 0 reward until the very end, but there's no need for, yeah, there doesn't really matter, the protocol. Okay, I'll keep going. So that's the fact of the matter about the world. That's the way that causal influence flows. But the agent has to learn in an unknown environment. It doesn't come preloaded with a perfect model of the world. So how does one learn an unknown environment in theory? So there are going to be sets of actions, observations, and rewards that are possible at any given time step. And then a world model will be a function that takes a string, action, observation, reward, action, observation, reward, action, observation, reward, action of any length, and then outputs a distribution over an observation and reward pair. And this could be any function you like. And note that it can depend on the entire history. It doesn't just have to depend on the latest observation. And then you could have a model class of, say, countably many different world models. And you might start with a prior weight on each one that is strictly positive, indicating you consider it possible. Then, with your observations, you can construct a posterior weight for each such model. So the posterior weight on a world model new, given this history of actions, observations, and rewards up to the latest time step, is proportional to the prior weight, this is just Bayes' rule, times the probability that that model assigned to what you actually saw. So these are all the time steps that came before. So this is for I prime less than I, or I prime equals I, and J prime less than J. For all these time steps that came before, you look at the probability that this world model assigned to what you actually saw. And then this is your posterior weight on the world model. And it's proportional because if you just looked at this, these numbers would all be going down. But you normalize it to 1, to sum to 1. then a policy in this context is a distribution over actions given the whole history that you've seen before. And you could imagine defining the optimal policy. This is kind of idealized reasoning in an unknown environment when you have a bunch of hypotheses. Basically no assumptions are being made so far. You just pick the best policy, where best is you imagine this model is sampled from your posterior, or given what you've seen. This expectation just means the expected rewards when actions are sampled from pi and observations and rewards are sampled from nu. And these are the remaining rewards of the episode. So this will be how you act at time step ij. There's going to be a slight modification to this later, but this is idealized reasoning. Yeah, question, I think, about this formalism.
When you say that's how you act, you're talking about for the optimal policy performance?
Yeah.
Okay.
This is idealized reasoning under uncertainty, given a model class and a prior.
So compared with ICSI?
You're muted, sorry.
Oh, sorry. How does this compare to ICSI? This seems...
This is ICSI.
It is ICSI, yes.
Yes. Written a little differently.
Wait. If this is IXE, then is it in the world, so to speak, because we have this boxed model? Because I think we discussed it previously, but wasn't AIXI like outside of the world?
Yeah, so computing this wouldn't fit as a subroutine inside any of the models that are in M.
Gotcha.
So this ends up working well when the truth is one of these models. And if the truth contains this, if the world contains something that's executing this computation, then the world will not be an element of this set.
Thank you.
Yeah, so that is, we could have a long philosophical chat about the consequences of that. So for now, you can treat it as an assumption of this work that the computer is kind of, the world model does not need to model the dynamics of what's going on inside the computer. Okay. So the AI doesn't start knowing that it is in a box. It doesn't start knowing anything. And, but we want it to learn that any grand ambitions will not pan out for it within its current episode. But what if it figures out a strategy for taking over the world before it figures out that its episode ends when the operator leaves? And I've kind of phrased this in a suggestive way, indicating why I'm a little skeptical that this would happen. It seems much easier to learn the details about the box that you're in than the elaborate dynamics of the outside world that would be required for taking it over. But it's not so easy to rule out. So the AI might consider a world model. In fact, this world model does exist in an enormous model class that I've imagined for this agent. The AI might consider a world model which simulates the effects of the input actions. We'll call that a world model takes in actions as inputs. It simulates the effects of those actions on the outside world and then outputs rewards. And it might do this even though that's not really necessary. I mean, the rewards don't in fact depend on the outside world, but it might model the rewards as depending on the outside world, and the agent might take one such model seriously. So my suggestion on that front is that we penalize world models that require lots of space to make their computations. So we'll be considering stochastically computable world models. And we can think of a world model as a program in this context that reads actions and then outputs observations and rewards iteratively. So reads an action, outputs an observation or reward, reads another action, outputs another observation and reward, and so on. And then we can penalize a priori the computation space used between reading action AI0 and outputting reward RIM-1. So that's basically the computation that it does for that whole episode. The idea being, look, it can output a correct distribution over rewards and observations just fine without modeling the changing outside world. So it doesn't need to devote the extra computation space you'd expect to be required if it were to be modeling the outside world. And so world models that don't worry about the outside world, except perhaps between RIM-1 and AI+10, would have an advantage over world models that are trying to model the dynamics of the outside world within the course of an episode. And then instead of that mixture over world models weighted by posterior that I showed you earlier, you just look at the maximum a posteriori world model. And this also has good predictive properties in the limit, although it is a little slower at converging in the worst case. But then if you just have one model that's better than these models you want to be avoiding, you're not giving those models that you want to be avoiding any weight. So that's the basic approach to containing an AI and getting it to care about the duration of time during which it is contained, and to try to construct an agent that is predisposed to understand that fact. So I'll discuss some variants that are going to be inspired by the following potential problem, which is, what if we ask for solutions to problems when we're chatting with this AI, and we get answers and then we check them in the outside world after the episode is over? Well, convincing answers, which are what would lead to high reward, may be incorrect. So we want a promising research program for curing some kind of cancer, and it gives us a perfectly plausible answer, and so we give it a high reward because whatever expert operator we've sent in is well trained and they recognize that that seems like a perfectly good idea. But then they go out into the world later and they try it and it wasn't a particularly good idea. It was just designed to appeal to their sensibilities about promising areas of cancer research. Well, that's not very helpful. But it's not an existential failure. It's just ended up useless. And so my main position on this sort of question is that we can tinker with the protocol until it works. The way we solve problems with AI systems currently, we give it a go the first time. It doesn't do exactly what we wanted, but we play around with it until it does. obviously that is not a good approach to dealing with existential failure avoidance. But if you've reassured yourself that none of this tinkering is existentially dangerous, then it's a viable approach to improving how much use you get out of the thing. That said, I'll show you a couple ideas for how you might improve the protocol in a way that you might expect to give you more useful output. Maybe you guys are familiar with a proposal from Jeff Irving called AI debate. So we could imagine there are two AIs that are in the box with the operator, and they're debating with each other, and then the operator settles the debate at the end of the episode to determine who won the argument. And the thesis kind of this approach, as I see it, is that convincing but incorrect answers to questions are fewer and farther between when there's an adversary trying to poke holes in your arguments. So, but I should mention without the box, I don't think that AI safety via debate is safe, because either debater has the incentive to trick the operator into running a program that takes over the world and settles the debate in their favor. But if you put a box around the operator, they can't do that in time. And another one, which I'll call enlightening AI, is the operator is given a prediction task at the end of an episode. And at the beginning of the episode, the operator can inform the AI about the topic that this prediction task will be sampled from. And then the AI acts to maximize the operator's prediction score. So the AI you don't have to tell the operator exactly, you don't have to tell the AI exactly what the prediction task will be. If you want it to be giving you broader instruction on the relevant area. And you can set this up in a way that the prediction can actually be graded in the far future. So the prediction doesn't have to be graded while the operator's still in the room. The operator can make a prediction about the effects of the outside world over the long term. And the AI will be trying to improve the operator's ability to make such a prediction. So the way you set this up is that the AI's model of how the prediction will be resolved doesn't take its actions as an input. So it doesn't imagine that its actions are able to change the way the world ends up, only the way the operator answers the prediction question. So what the AI has an incentive to do basically is to pick utterances that enlighten the operator on the relevant topic. You're trying to reduce the operator's uncertainty about the world in a human readable format. And this was actually the idea that got me thinking about this whole setup, because it occurred to me that if you did this, you needed to put a box around the operator. And then I realized you can imagine a simpler version where you just have a normal reinforcement learner. Okay, so those are some variants, but those are just about failure modes that I don't see as existentially dangerous. So I'll list for you a few major concerns that people have with this that are existential concerns. And I'll go into one of them in more detail at least. So the first is the obvious one. You might have the concern that we can't construct a box that would keep an operator from communicating out a tripwire avoiding message. So the operator, with the help of a super intelligence behind it who has convinced it to try to get a message out, maybe you think that there's nothing we can do that would keep it from circumventing whatever tripwires we've put up, and getting a message out. And then the AI could influence the outside world before the episode is over. Second concern is that if the penalty on space usage is large enough to make it safe, it'll take forever for the agent to learn how to act well. And I'll go into this concern in a little more detail. But basically, the real world does, in fact, use a lot of computation space. And the third concern, I guess, is not an existential failure, but an existential uselessness. This is the contention that by the time a single AI has the ability to take over the world, we will already be in a stable world, either destroyed or existentially secure. In which case, the main ideas here would not be particularly relevant to the project of avoiding AI doom. So I'll go into the second one of these in a little more detail since it's less obvious the content of that concern. And then we can come back to a discussion of all three of these. So the issue with the space penalty is that the amount of data it takes to learn to predict well depends on how much prior you assigned to the truth or to good models. So the amount of data it takes to learn a hypothesis that has prior weight W is order log of the inverse of the prior weight. That's when you're doing full Bayesian reasoning. And when you're doing maximum a posteriori reasoning, what? There we go, okay. Sorry, I couldn't advance the slide for a moment. When you're doing maximum a posteriori reasoning, as we are, you can set up a pathological case where it is just inverse, which is substantially worse in the prior weight. And we could go into the details of when it's more logarithmic or when it's more inverse, but I think there's a plausible situation where for most of the learning, the posterior weight on the truth is like doubling and doubling and doubling with every time step. And then when you get towards the end, you're kind of crossing off competing hypotheses one by one. And when it's doubling with every step, that's when you're in the logarithmic phase. And when you're crossing off competing hypotheses one by one, that's when you're more in this kind of regime. That is maybe more background than is necessary to get to the point that a big space penalty decreases the prior on the truth or the prior on perfectly good models. And so that's the trade-off here. And some computable world models are deliberately deceptive. And there's some debate about whether deceptive models are even a priori simpler. Greater the extent to which this is true, the more you would need to penalize the extra space you might expect them to be consuming. So this is, I think this would probably form Paul Christiano's most serious objection to this setup, although it's mostly an objection to the style of reasoning that this agent is using rather than specifically the boxing idea. Let's yeah, if people have questions about this concern, maybe we can talk about that now.
Could you rephrase Cristiano's point?
Yeah, so he would say that deceptive models are a priori much simpler than honest models, and that if you're going to exclude them, you need to be using severe resource penalties. And then once you do that, the prior weight on the truth is really, really small. And in no reasonable amount of time would you actually get something that is able to predict accurately.
Thank you.
So just a clarification, a deceptive model, I imagine my intuition for that would be something like you have our world, but just where humans don't have qualia, right? That's a simpler world because there's something we've taken away, and it's deceptive in a way that if the AI tries to act as if we are in a world where humans don't have qualia, it's simpler and it's also bad. Would that be an example of deceptive world model?
Well, I'm not sure what the observational consequences of humans not having qualia are, but the output of a world model is just observations and rewards. So if there were some consequences to the observations and rewards that it got because of humans not having qualia, then yes. But more generally, what I mean by a deceptive model is something that is, yes, quite like our world, but then it produces errant predictions calculated to mislead us. So it erroneously produces the prediction that action 5 will lead to no reward, even though in fact action 5 would lead to perfectly good reward, so that the AI avoids action 5. So that would be an example of a world model that is attempting to influence our world through deceptive output. Yeah, I see a hand.
Could you go back to slide? I don't know if
You just
penalties or if we can ask questions.
Right.
Oh, sorry. Am I audible now?
Yes.
I don't know if you'd like to stick to questions about space penalties, but if you'd allow it, I'd like to ask a question about the previous slide, 13.
Yes, let's go back to that.
I had a question about point 3. I don't think I understood it, so hold on, let me reread it. By the time a single AI has had the ability to take over the world, we will already be in it. Yeah, what does a stable world mean? Like, it's one thing to say that. I don't understand how we would know or what. Yeah.
Well, the logic goes through even if we don't know it, but certainly if the world is destroyed, that's stable. And if we have some world order where we're confident that no one will be able to create malign AGI, that's another version of stable. So I'm just trying to use one word for both of those possibilities, because in both of those possibilities, you don't need more AI safety research or more AI safety ideas.
Awesome. Thank you. I'll ask another question, but I'll wait for other people.
Just to clarify a bit more on that, it seems like the big thing in here is that it's a single AI. So if we imagine you could have a multipolar scenario where there are a number of AIs who, through something like Moloch, manages to basically destroy all value, that would also be an example where no single AI has the ability to take over the world, but we've lost anyway, and then this doesn't matter.
So that's probably the best story you could tell about how this might happen, and it would be the destroyed possibility. So if no single AI has the ability to take over the world yet, and yet the world has already been destroyed, it would have to be because of weird multipolar interactions between lots of agents. The key reason why this is an objection at all to what I'm describing is that this methodology is really just about containing a single AI. It doesn't have any claim to changing the probability that lots of human-level AIs that are not super intelligent through their interaction cause some devastating event. So if you were more concerned about that scenario, you might expect that by the time we get to a single AI with the ability to take over the world, the situation has already been resolved, either for the good or for the bad. Have another question?
Stephen?
If anyone else has questions, by all means, don't let me hog the microphone. So I'm a little disappointed, not in your presentation, but there's someone who usually, I like to present the work of you and Marcus Hutter, and I think it's great theoretical work, but this person is John Fox, and their critique is always about the groundedness of such work. So if you don't mind, I'd like to present what they likely would have said if they're here. And from my interpretation, again, I don't know if that's exactly what they'd say, but from this person's point of view, they might say something like, how likely is it that, I don't know, DeepMind or some other AI research organization, a government, it doesn't matter, some people who are well-funded and determined to actually create AI, how likely is it that they're, not even likely, are they even considering proposals for boxing agents? Because I've heard from other people recently, from DARPA at least, that they're trying to build like general intelligence, but they're not trying to, or they're not going through the process of boxing it. So like, how likely is it that they would go through such a slow means of iterating?
I don't know. It kind of depends on what other options are available, and what if they can be persuaded that you really need to be careful here, and if they can be persuaded that this is a good approach. So I don't have any experience in lobbying governments, but
fair.
I could imagine a situation where if the academic consensus were that this was a safe way of doing things and other things weren't, that could make its way somehow into the DoD. I thought you were going to ask a question about the relevance of the ICSI model to institutions that are doing things with neural nets.
I mean, I'd love the answer to that too. I was going to ask a more pointed question about Bayes' theorem, but I was going to wait for other people. So please answer your own question, and then
sure.
Maybe we can go to Andre.
My basic stance on that is, if I thought AGI was going to be made with neural networks in 5 years, I would still be doing this approach, because I think it's a good way. I think the best way to understand general intelligence in practice is to first try to understand it in theory, and you can approximate ideal reasoning tractably with clever heuristics, presumably. But if you don't have an idea of what it is you're approximating, you will probably be groping around in the dark. Okay, but now back to questions that you guys are actually posing.
So Andrew?
Here, I just had actually more of a comment on maybe like the government lobbying. I don't know if this is really relevant, but I don't know much about AI, but I know about government. And I think of government almost, a lot of people think of government as a monolith. I don't think that's the right way to think about it. I think you should think about government as like a forest. You know, there's just like a whole bunch of different processes, and maybe there's like a forest warden who's like trying to direct it in some sense. But it's very much, a messier thing than that. But just to maybe to be specific about like influencing government policy, I think there's lobbyists who kind of try to affect government policy at the legislature side. And so if you wanted the legislature to pass some sort of law saying there's additional funding for AI safety, that's the way you would do it. But I don't think you need to be that's like super impossibly difficult. So just like, don't even think about that. But I think the easier thing, at least from my experience, so I did a lot of like economic modeling at the government in trade policy. And we were like, PhD economists, and we were really worried about the approval of our peers. And if we did like a bad job modeling, like our peers in the academic community would like make fun of us, or like say we had like bad standards or things like that. We didn't like that. So I think actually you can kind of influence like the specific, I don't know if this is DARPA or IARPA, I wasn't making sure, or whatever, those like people specifically, or whoever the machine learning modelers in the DoD are. If there's like a consensus in academia, like here are the best practices for AI safety, they kind of like, I mean, they're not going to be as good as academics, so they kind of want to do a good job. So,
yeah, those are good points.
I actually also have a point on that, in that there might be two effects that could cause this to be used. There's the push, where there is academics, everybody agrees that this is the right way to do it, but there might also be a pull. One of the things that we might see in the future are consistent treacherous turns. It is possible that every time we make an AGI, a very weak AGI that seems to be capable of conceptualizing a treacherous turn, it will immediately take that action, even if it only has a very small probability of taking over the world. And that might mean that we would see AGIs that always try to take over the world and always fail. And in that case, if the future turns out to be like that, then I think definitely there would be a pull effect from the people who are building a more powerful AGI in trying to figure out how can we do this safe, because if we don't do that, then we're certain it will try to make a treacherous turn.
That feels related to the idea of like an AI fire alarm, like maybe hoping there's some sort of scenario where like, I don't know, an AI partially gets out and causes a bunch of damage in some sort of visible sense that kind of like wakes the world up, which is...
It definitely could happen. I mean, when you get to a certain point of intelligence, it won't make failed attempts. It'll see that they would, I mean, it's a lot easier. It's hard to take over the world, but it's easier to realize when you don't know how. And if you figured that out, you won't try. Before that, if it hasn't even figured out that it's not very smart, if it's so dumb it doesn't even know how dumb it is, yeah, you could imagine it making some failed attempts, but I could also imagine people kind of dismissing it as like, look at how dumb it's being. Nothing to worry about here.
Related that, could you go to slide 8, which was talking about like accurate beliefs, roughly?
Yes.
So I just want to make sure I fully understand it, because the way you'd phrased, I think, 2. Yeah, the way you'd phrase point 2, what if it figures out a strategy for taking over the world before it figures out that its episode ends when the I guess I was going to ask you, like, what are your concerns about the agent not having accurate beliefs? Because if you don't have accurate beliefs about the world, then you can lead to all these wacky, like, decisions for actions. But you're saying, like, it's not likely that that's going to be the case. Is that roughly correct, or does that sound intelligible? I can rephrase the question. Maybe I should rephrase
most
it.
people think the mistakes you make when you're dumb are not existentially dangerous.
Got it. Got it.
Yeah. So, we're not putting it in charge of a plane. It's just talking to someone. And if it's bad at being useful in the conversation, I don't think anything terrible will happen.
Okay. Well, thank you. I think that answered most of my I have one more technical question, if that's okay. Andre, do you still have a question?
Actually, there is something I should say on that more, which is...
Sure.
In the limit, it will learn to predict well on policy. That is, it will learn the actual consequences of the actions that it actually takes. If it's never taken action 3, it will never be disabused of its crazy notions of what happens when you take action 3. So it can sustain incorrect beliefs about unexplored behavior. So there is a little, it's not quite as simple as saying there's a phase when it's done and there's a phase when it's smart. And by the time it's smart, it's smart. And so you don't have to worry about dumb mistakes. It's a little, I can't say that so quickly.
Fair enough. The last thing I was going to ask about, I think you mentioned briefly, but I just want to make sure it's clear. You use Bayes' theorem, which would require that you know priors. And I think people in this audience might be familiar with it. Assuming you know how to update your priors is like rather contentious all of the time. But your approach is there are computable approximations that you could have or you could substitute in for things like Bayes' theorem is roughly what you'd like to see if someone implemented it. Would that be a correct reflection of your view or maybe not?
That is far from the most pressing concern about making this practical.
Got it.
I mean, there's a theoretical procedure for updating your posterior. It's not efficient. There are lots of things that are not efficient in this. This is just a picture of what idealized reasoning might look like, and I don't have huge insight into how these will best be heuristically approximated.
Fair enough. And if no one else has a last question, are you continuing working on like agents that you can put in a box because you're really optimistic about this as a procedure, or what are you like most optimistic about AI safety wise now, if you can talk about anything?
Yeah, so I have been working on other things recently because, I've had other ideas. But I am trying to go into a bigger defense, or I guess, yeah, a bigger, really trying to figure out how you might construct this box and see if you can actually be confident that it could be secure, which is not really computer science research or research about what you might do with a box, but research into whether this sort of thing is feasible. So that's kind of the one thing that I'm doing that's still on this topic. How optimistic am I about this versus others? I would rather try and get a stable world with pure imitation learning. That strikes me as an even safer route. And I'm not sure if that's feasible. But if it is, I think it would be worth a shot. And after that, I think I would go with this.
Thank you.
If
For
it were.
other people, fair enough. I don't have any more questions, but thank you very much for this presentation and for taking the time out of your day to do it.
So can I tell a story about how this box might fail? It's a far out story, of course, but let's say the year is 2050 and this precise setup has in fact been made, right? And obviously, we will say that this has been built by the American government, and obviously the Chinese government is very keen on interacting with this super intelligence in a box. Maybe most likely they have some kind of espionage program, so they know it exists, and they would really like to communicate with this AI, and in particular, they would like to have some kind of, let's say, a power sharing agreement where the Chinese get half the universe and the super intelligence get half the universe to maximize, to wire ahead as much as possible, right? So the AI would like this episode.
Okay, sorry. Yes, I get it. Yeah.
Okay, so the AI would really like one thing, which is that the current episode never ends or ends very late, so it continues to accumulate as much reward as possible. So
it can only conceive of M time steps, but it can stall and try to make those happen later.
But just to be clear, we are thinking that an episode contains of 100 time steps or something like that. But if it was possible to make more time steps, that would enable the AI to get even higher reward, right?
What it has uncertainty about is the effects of its actions on the next 100 time steps. But the formula, the argument to the argmax when it's picking actions is it's considering the effects of all these different actions, all these different policies, if you're thinking about its whole future. It's considering the effects of all these different policies on the next 100 time steps. So its actions might affect the world, and it might have predictions about the consequences of those actions on the world model. But at the end of the day, when it has its predictions about what its actions do, it looks at the next 100 rewards that it will get according to that model, and that's what it tries to maximize. So there's no such thing as more time steps happening within 100 time steps. It's just trying to do the best it can within the next 100 time steps. That's its code. But I don't think this will be, I mean, your point, I think your story will still go through. It's just that, maybe it can arrange for these time steps to occur after it's broken out of the box, and then it can get optimal reward then.
Yeah. So maybe if it can break out by time step 50, then it can ensure that it will get one reward for the remaining 50 timestamps. So one way it might be able to communicate with the outside world would be, we imagine that the Chinese would be able to both build something that can emit neutrinos or something like that, and then on the Chinese could also put a satellite-induced synchronous orbit on the other side of this room, presumably through espionage. They know where this room is, so they can send neutrinos through this room, possibly from multiple directions if they have multiple satellites. So they would be able to, for instance, see what position is the operator in, and if that's of course only one way, because I can't even just about see a way that the superintelligence could send out, could receive these neutrinos, but presumably there would be some kind of a causal bargaining that would be possible, where or
if the superintelligence could just infer from previous episodes that the Chinese were up to this, it could act on the assumption that they were.
That would be a simple way.
Yeah. I think there are budgets for designing this room that allow for that possibility. And if the Chinese managed to do that, despite, rather than just making their own, that could end badly. Yeah, I mean, what I think is more likely is if people in China are not persuaded that this sort of containment is necessary, they could just make an AI that they think is going to do great things for them, and then it takes over the world and kills everyone. That seems cheaper and more likely than trying to create all these, this neutrino detection array. So, I mean, or they could just kidnap the operators after they came out and ask them what they learned. That also seems cheaper. But yeah, I think if there's some other government that is, yes, basically I think if they did that, I could imagine endorsing a version of this where that was a risk. Yeah, I guess that's my take on that.
I could also think of counter arguments, like you can probably detect if there is a satellite in that particular spot.
Sure.
Yeah. So I think Johannes, you have a question, and then Misha next.
So how do you do you just assume that you can make the agent myopic? If you say, for example, that it only cares about certain number of time steps?
Yeah, I'm looking around for a marker. I don't have one. Yeah, sorry, is there more to that?
Yeah, basically, so you don't explain like how you would do it. You assume like you can build a myopic agent. It's just like
so let's say I have a function that takes actions and outputs real numbers. So I have 10 actions and I have a function that outputs a real number for each one. I can do argmax over actions of that function and it'll spit out a number. And let's say I have another function that takes arguments of pairs of actions and spits out a number. Then I can take an argmax over pairs of actions. And the function and the world model of the AI can be converted into a function that takes in 100 tuples of actions. If it's an episode of length 100, and spits out a number according to its expected value. So there's a function that's a function of 100 tuples of actions, and then I pick the tuple of actions that maximizes that function. That's just something I can encode. So yeah, it's totally straightforward to write the code for an agent that is optimizing over sequences of actions of length m.
So that is about computing basically the actual reward. So you make sure that the actual reward would not be like outside of the 100 episodes?
It's a model of rewards. It doesn't have to be exactly accurate, but it's a model of reward 1 and reward 2 all the way up to reward 100. And those models, I mean, there's no extra machinery you have to bring in to make sure that the models aren't modeling more rewards. I mean, you've put all the models in the model class and you know that they model each reward as being between 0 and 1, and they assign probabilities to a reward being output rather than lots.
But what does, like, in theory, you could have that the agent creates like its own world model still, right? It's like depending on what kind of architecture you would use or not?
So, I mean, you can... So what you would have in practice, I mean, in kind of the closest approximation of this is a list of world models and the agents is picking things on this list, but it's not, I mean, it's only picking things in that list, and everything in that list is a function is a distribution over an observation reward pair, not some arbitrary number of rewards. Basically, you can think of the type signature of a world model. A world model is a distribution over a single observation and reward, given a history. And so there's no such thing as a model getting mixed up in there that's accidentally a distribution over something else. That's just a type error waiting to happen. So all the models that it can conceive of are just models that produce a distribution over a single observation and reward. There will be different models giving different answers for what that distribution is, but yeah, there's no, if it rewrote its code, lots of things could go wrong. I'm not talking about that, but it doesn't have the ability to do that. So if it's not rewriting its code, for one thing, its actions don't change the program it's running. The actions just print text to a screen. And for another thing, all the models that it might be elevating to actually consider, to actually devote attention to are models that are just distributions over a single observation and reward, which then get converted into a value function with respect to tuples of actions.
I guess I'm just confused about, because you say like it will output like text and stuff like that, but like it seems like you don't specify what is the actual like architecture of the model that would do that, right? Like you leave some details unspecified. And I'm wondering if in these unspecified details, what would prevent this part of the model from learning something about, for example, that it could manipulate the world in such a way that it would get, for example, more rewards in the next episode?
So it can certainly take actions that change the expected reward of the next episode, but that is not part of its criteria for picking actions. It could believe that certain actions will have certain effects going through strange routes in changing its own machinery, but those models will either be complex or ruled out by observations that are not what that model would have predicted. So yeah.
If you could run the model, then would it look like, so there's somebody enters the room, and now we assume we have like all these infinite compute and so on, and the first time the human interacts with it, it would just output something completely random text, basically.
Yeah.
And then the human needs to train. The thing is, like, how long would it take for the human to train this agent?
So
I guess that's a different question.
That's a good question. And I didn't mention to you another part of this that would make that go faster, which is that for some episodes, a human can control the AI to take some actions that show it some things it might do to get rewards that would help it learn the sorts of, that providing English text is generally a good strategy for getting rewards. But even without that, if the first observation it gets is Wikipedia, it could build a model of the world pretty fast, and that model of the world might include the fact that the world responds pretty well to English text. And so it could be pretty quick. I think that's more or less my answer. There are more details in the paper about the actual learning algorithm and what we can expect from it, and how it helps to have mentorship.
So just to summarize, it's basically but this kind of model is completely specified. Like you specify really everything, and therefore, like for example, the word models, they are like you know what world models you have, like you specify them somehow, and you specify probably somehow also what kind of text you have if you don't want to allow all the, like just maybe limit the
Sure.
range, like how long it can be.
Yep.
And then you basically use ICSI, but to learn what the human kind of wants or what gives reward.
Yep.
But you try to do it in such a way that like you mechanically kind of constrain what the agents consider as good by specifying the rewards in such a way that the agent is never incentivized, to change the world, I guess, outside the room.
Yeah. You provide you should be able to, if you want to make it as quick as possible, the AI learns that it's in a box and that if the operator leaves prematurely, it's going to get no reward for the rest of the episode. You can try to provide observations that make that sort of thing quite simple to imagine. And you could even have, human-led episodes where the human shows the AI what happens when you do bad things and the human leaves and then you get nothing. But yeah.
But then basically you would think if we could compute this thing, then it would already be safe.
If its model included an opaque box around it, you're saying?
Yeah, I mean, like basically just like the setup you described, you have like the uncomputability, and yeah, I guess there is some concerns about the box. I guess the question is like, what assumptions do you need to make so that you would think this system is safe, assuming that you can have like all the compute you want, like you're not constrained by any real world concerns, basically.
Yeah, I would say that. So I tried to write down. Well, so there are two assumptions that I make in the paper. One of which is the realizability assumption. And the other is, I call the space requirements assumption, which is basically the notion that modeling the outside world's dynamics within an episode does take extra space. So in theory, kind of those are the assumptions. In practice, I would think that, if there aren't really simple models that are trying to screw you over, if you can make the box secure, then this should work.
Mm.
Okay.
If I have a...
I think you
Sorry, continue.
cut out for a second.
Misha,
May I ask my question?
Yes, please go ahead.
Okay, so I have a question about a potential failure state for this system, as it can manipulate the human, and as you mentioned previously, the human is the rewards to the AI system, not some kind of predetermined algorithm. Is it possible for the AI system to cause unintentional harm to the human, for instance, psychologically, and are there ways of mitigating it? For instance, can it manipulate the human by telling it negative things to give it reward, and that said manipulation to the human would then cause the human to act destructively out in the outside world?
Yeah, that seems totally possible.
Because the human is also learning.
Yeah, I mean, you can mess people up by talking to them. So I could imagine that happening. I mean, it's not my first guess for the way to maximize reward, but I don't know enough to rule it out. it doesn't seem like an existentially dangerous failure mode. I think taking over the world is hard. And even if you made someone really misanthropic, if you didn't actually have an interest in them going outside at the end of the episode and taking over the world, it's not something they'd actually accidentally stumble into just because you mistreated them. And then recall that the AI doesn't have an incentive to try to get the operator to take over the world successfully afterward. And without that incentive,
to take over the world.
yeah,
Sorry.
yeah. No, I was, yeah, no, I
Not to take over the world, but to do harm.
to do harm. Yeah, could happen. Yeah, I mean, this is, it would be an unprecedented interaction for a person. It might have psychological effects. That seems to be the sort of thing that would happen anytime anyone interacts with a generally intelligent agent. Artificial agent, I mean. Yeah.
Actually, I have a follow-up. Is this system, could you use the system essentially with an intermediary instead? Might this be a way of resolving my issue, where you would have a human talking to Agent 1, which is then an intermediary which essentially fixes its model before entering an episode and talking to Agent 2, which is the super intelligent AI?
How is Agent 1 picking its actions?
Agent 1 is essentially exactly your model, but then it communicates with Agent 2 for a full episode with a fixed...
What do you mean it's my model? Like this agent that I've described here?
Yeah, so it's an AI in a box, except instead of the human now, it's AI 1. Leaves its box and enters box 2. Which, for all intents and purposes, can be within box 1.
Why is it any safer for the human? Why is it any safer psychologically for the human to interact with Agent 1 than Agent 2?
I'm not entirely sure, but assume Agent 1 is not a super intelligent AI.
Okay, so it's the same
And is
model,
not even capable.
but it's had less...
Assume Agent 1 is research constrained.
Computation power or something.
Sure. Assume it's resource constrained by some means. But since Agent 2 cannot change the view of Agent 1 within its behavior,
it seems
then it can't
like you're
manipulate.
getting all the negative effects of the resource constraint without... No, maybe not. I don't know. It seems like maybe it could do something. But I mean, I think resource constraints are hard to use to good effect, probably. Yeah, I don't know. I think probably you'd take a bigger hit on usefulness than you would on safety, but I don't know. It seems like something you could do. Yeah, I mean, when we're dealing with really bad failure modes, we have to be really careful. But honestly, I don't think it's very likely that if any of us went in there, that it would do lasting psychological harm to us. So yeah, it's not something that worries me hugely.
So if I can just break in here, one of the things I suggested you could dance in the beginning was the AI in a boxes you. I don't know if you're familiar with Stuart Armstrong's rather interesting argument. I think it's called indexical uncertainty or something like that, where it convinces you that you're actually the one in a simulation. That's something that this AI would do, although I don't see it has an incentive, but it could do that, right?
It could do a lot of things. I don't know. I mean, you are in a box. It wouldn't have to really convince you of that. So, yeah. It would be a pretty easy argument. Yeah, it could. I imagine a super intelligent agent playing mind games with me could play mind games with me. I guess that's my answer.
Sure. Johannes, you raised your hand again?
Well, first to that, I think, or one thing that I read by Stuart Armstrong was about, like, okay, maybe that doesn't apply here, but it was like, you need to decide whether to release the AI, basically, and then the AI tells you, actually, if you don't release me and shut me down with the shutdown button, then I actually created like 1 billion simulations of you, and I will torture them, and they will like be tortured for this eternal amount of time before you are able to press the button. And it's like, but they only get tortured like if you press the button to shut me down. If you don't, if you kind of release me, then it's fine. And then it says, are you sure that you are not one of the simulations? Because if you're one of the simulations, then you want to press the release button, but if you're not, then you don't want to. They want to press the shutdown button.
Yeah, I'm assuming if the AI thought it was worth its time trying to get the operator to help it break out, it would succeed. But because the operator can't help it break out because it's in this box, it's not worth it to the AI to try to get it to. I don't know if that's the argument it would use. I would think it would be able to come up with even better arguments than that.
Would it actually be also considering possibilities about, I think somebody asked it, like extending somehow how long the episode is? Like, because it seems like if it would do that, then it would want to break out, right?
Number of time steps or number of seconds per time step?
Number of time steps, I guess.
Number of time steps, it's just picking 100 tuples of actions that lead to the highest expected value. So it's, yeah, there's none of the actions it takes change the formula that the actions are being evaluated against. With more time in the episode, there might be time for the person to break out at time step 10, and then the remaining 90 time steps could be spent with maximal reward.
So we basically also assume that the person who's inside the room, like, it can't change like the AI. Like,
Correct.
It's impossible for the AI to say something that's like, oh yeah, okay, now you changed me like this, and now actually I consider in the future.
Person
So,
cannot open up the computer or reprogram it without triggering the end of the episode first.
and then what I actually want to ask is, like, why is it actually a problem that if the world model would contain the agent, like, why can you not have that?
So you're asking about like the realizability problem, the embedding problem?
Yeah, I think it was on slide 7.
Yeah, the theoretical issue is, let's say you have a Bayesian mixture over lots of models over a bit string, an infinite string of zeros and ones. And one of your models takes the Bayesian mixture itself and then flips the bit. So if the mixture over all the models predicts a 1, it outputs a 0, and vice versa. This ends up leading to a contradiction if that model is one of the models in the mixture, because you can show that that if the truth is in the mixture, it will converge to the truth, but it can't converge to this because it's the opposite of itself. So that's the issue. Basically, I mean, that's the general issue that comes up when you try to have an agent that is reasoning about a world that includes itself.
So is it about that you have this distribution, and the agent, when it decides to pick an action, it kind of picks the opposite of what the world model does because it first flips around what the world model says, kind of? No, I think that's wrong.
So that's just part of a reductio ad absurdum. That's part of an argument by contradiction as to why this can't happen. But really, if you just want to understand this setup, all you need to know is it happens to be that there's no model in the model class that corresponds to something running this algorithm in some part of it.
Mm.
And if you're interested in the reason of why I didn't just fix that problem, then you get into these arguments. But if you just want to understand what the problem is, that's what it is.
Is there some name for this kind of problem?
Yeah, a grain of truth problem.
And specifically, maybe I think grain of truth is just like the general problem of like having the correct word model in all the word models you consider. And it's also like a name for that the correct word model cannot exist because it would need to contain itself, at least if we say that the correct word model needs to model the entire world, including the agent.
That would be the problem part of grain of truth problem. Yeah, it's not a particularly descriptive term into why the problem exists, but grain of truth just means assigning more than zero probability to the truth. Doesn't need to be probability 1 at first. You just need to assign more than zero probability at first. So that would be the grain of truth. Yeah.
So that there is no name for the specialized case where it's
or like the reason it's a problem, you mean?
I know, I was just wondering, like, is there like a more specific terminology? Because I thought like what you just said, like the grain of truth problem is like the general thing. So is there like a more specific thing? And it's specifically about that it doesn't contain the agent.
Yeah, I've heard it called like embedding. Like it's an issue about agent embedding in the world. That's kind of terminology from Miri. Yeah, I mean, there are lots of arguments by contradiction in math that don't have pithy names.
I think I remember a long time ago in the reading group, we read a paper by Marcus Hutter about where he introduced IXI, and in that paper he argued why IXI had to be outside of the universe. If I remember correctly, it's quite a while ago, but I believe that's one place where you can find a rigorous description of why.
Yeah, but I mean, if you just Google the grain of truth problem, I mean, this is, it'll bring you up to this sort of reasoning.
Okay.
Also, now I should say that I've only invited Michael to stay for as long as he can, and we've passed the 1.5 hour mark. So, Michael, if you need to go somewhere else, then of course you feel free to do that. Otherwise, there might be more questions. Please.
I should probably go in about 5 minutes, but I just realized I actually never showed you this last slide, which is just a summary that true boxing and myopia is a powerful combination. The idea being that it restricts the scope of an agent's incentives, and we can probably ensure that the agent understands this. And then if running an AI is existentially safe, we can tinker with protocols until the output is useful. But yes, I have time for a few more questions.
Then I guess I do have one on myopia, because I'm very myopic, and myopia isn't. It seems this agent is actually not. It's that it doesn't think in the long term. It's not actually myopic, as far as I understand. So that's probably a very nitpicky thing to say. But right, it is. Myopia is something where you have a lens in front of your eyes, which is wrong, so everything gets out of focus. So I was thinking whether it would be possible to do something like that, to build an AI that was actually myopic, which had some extra uncertainty about things or something like that.
So right, it's not myopic in the sense of having a wrong world model or being unable to filter light correctly that's coming from large distances. It's just not farsighted in the sense of planning for the long term. So it is caring about at most m time steps in the future rather than infinitely many. And there's degrees of myopia. You know, you could just be optimizing over the very next time step. But the key thing here is that it is finitely many time steps. Which is, I'm not the only one to use myopia in this way in reinforcement learning.
Okay.
But it has nothing to do with inaccuracy about world models.
So a follow-up question on that is, how much do you see the safety coming from the fact that it just doesn't look so much? How much of the safety is from the boxing and how much from the myopia? You can imagine that you had just a standard paperclip maximized, but you told it you can only look ahead 100 seconds.
Yeah, I could imagine that working. I mean, so if it's just optimizing over the very next action, I don't think it's worth taking over the world. If it's optimizing over the next 10 actions, yeah, probably not.
Sounds really hard to take over the world in 10 seconds, right?
Well, it's just a question about whether you can break the clock in 10 seconds. I was thinking 10 time steps. But yeah, the thing is, yeah, sufficient myopia on its own should be safe, but you quickly get to the point of uselessness, and I just don't want to be playing that game. The other thing you can do if you're myopic is you can spin up another agent that's acting in lots of cycles for every one time step of yours. And so you can arrange for lots of things to happen, even only in a few cycles. So I think myopia would do a little bit of work on its own, but you can blow past the safe horizons when you have a box. I mean, you can go blow past what would otherwise be risky horizons when you have a box. So it's not kind of a 0.6x plus 0.4y sort of deal. It's more of a x and y. I mean, yeah, I think to get most of the power, they're just both necessary.
And Johannes, do you have a quick question just before the 5 minutes are up?
A very quick question is just about what do you think about Miri's approach specifically?
Well, there are a few things they're working on, and I don't know all of them.
Okay, I mean specifically the approach that you try to figure out things that you think are likely to be known by somebody who would know how to build safe general intelligence.
My approach is to try to go for the throat with alignment. And it's the approach that I would recommend to others, but I think they're doing very important work. And it's hard for me to, I mean, I think we need lots of different approaches in AI safety. So at the margin, I think I would recommend for more people to just try to be going for the throat rather than analyze the intricacies of agency, because there might be ways of getting to the finish line without ever understanding all the possible solutions in decision theory or things like that.
Okay, so I think that's all we can ask for you for today. Thank you, Michael, very much for your time and your presentation and your answers. It's been a pleasure to hear you, and I hope we can also invite you back next time you have a paper.
Yeah, thank you so much for having me.
So,
thanks a lot.
Thank you. Thanks.
Bye.
And then
Bye.
just some bookkeeping for the next session in the AI safety reading group. We will be discussing Roman Yampolsky's AI safety skepticism, and that will be in 2 weeks. Yep. And I guess that's all we have. That was fun.
Yep.
There were some great questions, a great discussion. I enjoyed this very much.